Okay, so last video we ended up talking about the expansions of sine and cosine of x in terms of Taylor series, and we talked a little bit about how we can use basically Taylor series to solve the quotient difference and everything like that. But okay, so now today I want to focus on some more applications to Taylor series. And as you can see, Taylor series is just a marvelous tool to pretty much everything. For example, later on in the videos, I'll talk a lot about differential equations, and you love Taylor series when you do differential equations. But for now, it's a nuisance that we have to know, and it's a very beautiful nuisance. Okay, so I want to do some more examples with you guys, and one of the examples. Actually, two examples. One of the examples is an integral question. One of the examples is a limit problem. So, in the previous video, we said we derived that sine x is approximately equals to the sum of k equals to 0 to infinity, right, of minus 1 to the kth power x to the 2k plus 1 over 2k plus 1 factorial, right? We derived this. And when we derived this, we said, well, and we derived this, and when we did a problem, we encountered, and when we did a problem, we encountered a special limit. A special limit. We encountered a special limit, and that limit was, and this was the final limit. So this was the limit. And and we said this was equals to 1. I'm gonna prove this using Taylor series. All right. So if sine x, right? If sine x is equals to x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th, and so on. Alright, and so on, right? Then obviously sine h is going to be just h minus, we replace every x by h, right? So we get this. The limit as h tends to 0, right, of h minus 1 over 3 factorial h cubed plus 1 over 5 factorial h to the 5th, and so on, right, plus over h, right? And if we see this, we can factor out an h. This is the same thing as saying the limit as h tends to 0, right, of h times 1 minus 1 over 3 factorial h squared plus 1 over 5 factorial h squared h to 4th, and so on. All over h. We can cancel out the h, right? And what do we get? Well, we get this. We get that the limit as h tends to 0, right, of 1 minus 1 over 3 factorial, right, h squared, right, plus 1 over 5 factorial h to the 4th, and so on. But realize that if you plug in h is 0, right, well, look what happens. Everything disappears, and so every higher order terms of this is just going to be equals to 1. So ultimately, the limit is going to be equals to 1. Right? This is a beautiful proof. that we can apply Taylor series at. And another thing we want to know is because of this Taylor series expansion, we can evaluate certain impossible integrals that we weren't able to evaluate previously. One of those famous examples is the indefinite integral of sine of x squared dx. And we're going to talk about techniques of integration later, but even with all the majestic techniques that you can learn in calculus of integration regarding integration, you cannot evaluate this integral whatsoever. Substitution is not possible. Integration by parts is not possible. Really, nothing is possible. And this is actually a really ugly integral to evaluate analytically. But we have Taylor series. I mean, God love Taylor series. So let u be x squared, right? Such that sine u, right, is equals to u minus 1 over 3 factorial u cubed plus 1/5 factorial u fifths plus o to the u sevenths. And I'm going to introduce this notation right over here, right? And what this notation means is, it's very simple. This is something called I'm going to use this side. This is something called, it's called the Bachmann-Landau notation or infinite asymptotics, but for now you can think of it as higher order terms. Higher order terms. So higher order than 7 and so on. So you can be u minus 1 over 3 factorial u cubed plus 1 over 5 factorial u to the 5th plus o u to the 7 plus 1 over 7 factorial u to 7 and so on. Right? Okay? So you can think of this higher order term, but originally this is something called the Bachmann-Landau notation. Landau notation, also known as infinite asymptotics. But okay, so we have this. So if u is x squared, right, sine of x squared is what? It's going to be x squared, right, minus 1 over 3 factorial x squared to the 3rd power, right, plus 1 over 5 factorial x squared to the 5th power plus o u to the 7th, right? Note that the only thing that we did was plug in x squared to u, because we said u is equals to x squared, okay? So that's what we did. We only plugged in u. And note that this, to be true, means sine of x squared, right? So it's actually equals to x squared, right, minus 1 over 3 factorial x squared to the 3rd is x to the 6th, right, plus 1 over 5 factorial x to the 10th plus o u to the 7th, right? All right. We cannot integrate this term. But we can integrate this term here. So, ideally, right? Ideally, the integral of sine of x squared dx, right, it's the same thing. It's not the same thing, but it's approximate to the same thing as integral of x squared minus 1 over 3 factorial x to the 6th plus 1 over 5 factorial x to the 10th plus ou to the 7th. dx. Maybe we don't know how to integrate this, but we do know how to integrate this. I mean, come on. So, evaluating the integral is going to be 1/3 x cubed, right? Minus 1 over 3 factorial times 1/7 x to the 7th power, right? Plus 1 over 5 factorial, right? 1 over 11 x to the 11th power, right? And so on, and plus so on, right? Plus higher order terms, and plus c, right? So we can definitely integrate. We can definitely find an approximate integral or approximate solution to this kind of integral using the Taylor series. Right, and this is one of the great uses of Taylor series. All right, and so now that we know what a Taylor series is, let me introduce you to something that I don't really introduce people to, and something that you've already learned. And these are the rules of differentiation. And in basic calculus, I'm sure you learned this. I mean, everyone learns it, but I'm going to teach you some additional tricks that you don't learn in basic calculus. Let me open up a document and my lecture notes, and we can continue from there. So if I open up my documents, I'm going to go down, down, down. If I proof my documents, okay. So, as we know from basic calculus, I'm sorry, I was opening my documents. So, if we know from the basic rules of calculus, we know that there are 5 rules. First is the power rule, and everyone knows this. Power rule, right? The second thing there is the product rule. The third thing is the quotient rule, and chain rule, which is another topic that we were going to really discuss about. And then there's the other type of differentiation called the implicit differentiation. For now, we're going to talk just about the power rule and actually try to understand what power rule really means. So the power rule says is that if you have a derivative of nth power polynomial x to the n, then the derivative of this is nxn minus 1. I'm sure you know about this. I mean, this is pretty obvious, but let's prove this actually. I mean, let's try to understand this. Let's prove this. Let's find a proof for this. So, to find a proof for this, just like any polynomials, we have to find the quotient. We have to find the limit. We have to make a limit definition out of this. So f of x plus h in this case, right? It's going to be x plus h to the nth power. Okay, and f of x is going to be x to the nth power. So by quotient difference, we're going to get something like this. Limit as h tends to 0 of x plus h to the nth power minus x to the nth all over h. Now, you can recall from pre-calculus that we can expand. So I'm going to make this in here. We can expand x plus h to the nth power using binomial series. Right? And if we expand, and so here's the rule. X plus y to the nth power, right? It's the same thing as n0 xn y0 plus n1 xn minus 1 y1 all the way up to nk xn minus k y, or here x0 yn. Right, so we start with x to the n, right? And then we end with y to the n. Okay? And we can see that and nk here is equals to n factorial all over n minus k factorial k factorial. Okay? So if we expand x plus h to the n, right? We're going to get this x to the n plus n1 x n minus 1 h all the way up to n h to the nth power. And if we plug this, if we plug this to the term of x plus h to the nth power, then we get the following. So we get the limit as h tends to 0, right, of n1 x n minus 1 h plus n2 of x n minus 2 h squared, and so on, all the way up to nn hn all over h. So let's see let's see this. Okay, so let's see it here, the first term. What is n1? n1, by definition, is equals to n factorial, right? And by definition here, which I wrote down here, is nk, so n minus 1 factorial times k factorial, which is 1 factorial, right? And therefore, this is the same thing as n1 x n minus 1 is the same thing as nx n minus 1. And x n minus 1. And the way how we got this equation here, the way how we got this equation right over here is, look at this. It's this. Limit as h tends to 0 of xn plus n1 xn minus 1 h plus n2 xn minus 2 h squared all the way, and if you subtract nn hn minus xn, right, all over h, you'll see that these two cancel out and we're left with whatever was here. With whatever was here, right? And this is the same thing as this, right? So eventually, if you do the algebra, I mean, if you do everything for this, when the limit as h tends to 0, the limit as h tends to 0 of x plus h to the nth power minus x to the n over h is going to be equal to nx and minus 1. So an example of this, and therefore the derivative of x to the n is equals to nx n minus 1. Alright. So an example of this is, suppose we have y equals x, 3x squared, right? dy dx is going to be 3 times 2 x2 minus 1. So another thing that we have to recall is that the derivative of some function of x plus another function of x, another function g, is the same thing as the derivative of f of x plus the derivative of g of x. Okay? So example of this is like this, the following. The derivative of 4x squared plus 5x, suppose, it's going to be the derivative of 4x squared plus the derivative of 5. X, which is going to be 8x plus 5. Alright? So this is about the power rule. And similarly, I forgot to mention, similarly, the derivative of f of x plus or minus g of x, it's the same thing as the derivative of f of x plus or minus the derivative of g of x. Alright? I'm sorry this video is a bit of a mess, but yeah. But I'm sure you got what I mean by here in this video. Okay. Now I'm going to talk about the product rule. I'm going to talk about the product rule shortly. Right? And the product rule states that if we have y is equals to some f of x, g of x, okay? If y is equals to some product of functions, then dy over dx is equals to f prime of x, g of x plus g prime of x, f of x. Okay? So, example of this is this. Suppose f of x is e to the x sine x. Okay, and the product rule of this, not the product of this. We can differentiate this using the product rule. So, suppose this here is f, this here is g. Okay, so this is equals to this. The derivative of f is e to the x, right? The derivative of g is cosine x, plus the derivative of g. Oh, no. It's e to the x, and g is just sine x, plus the derivative of g is cosine x, times f is e to the x. So really, this is just e to the x times sine x plus cosine x. Right? Another example we can do regarding product rule is f of x is equals x squared e to the x, right? If you have this, f prime of x, well, if you take the derivative of this, it's 2x e to the x, right? Plus g, so here, this is f, this is g, right? So the derivative of g is e to the x squared. So really, this is the same thing as saying e to the x, 2x plus x squared. Alright? Alright. Alright, now I'm gonna briefly mention the quotient rule. The quotient rule says this. If let h of x be f of x over g of x, where g of x is not equals to 0, So let h of x be a rational function, if we say mathematically. Where g of x is not equals to 0, because we have an asymptote and making it discontinuous and it will not work. Then dh dx is going to be equal to the g of x squared, right? G prime of x, f of x, minus f prime of x, g of x. Okay? All right? And if we do this, then we can find the derivative of a quotient if g of x is not equal to 0. And let me give you a simple example of this. Example, sine x e to the x, right? And we suppose this is equals to f of x, and suppose you have to find a derivative. So f prime of x, right, is equals to e to the x squared, right? E to the x times sine x minus f prime of x is cosine x times e to the x, right? So we get this e to the x sine x minus cosine x over e to the 2x. Alright? And we can simplify this further, but I'm not going to do that. And yeah, for this video, I think this should be it. I hope you found this fruitful, and see you next time.